Good morning, students. Welcome to Complex Analysis Live Lectures. In this class, we discuss one of the interesting result to calculate a value of a function at an interior point involving integral. So, namely Cauchy integral formula. Okay. So, what Cauchy integral formula briefly says is that so suppose you assume that you have a contour C closed simple closed contour. Suppose that you are given f is analytic, okay, inside and on those points, and if we have a point z naught which is an interior point to this C, okay, then the value of f of z naught, okay, is you can calculate this one as 1 by 2 pi I into integration of f of z upon z minus z naught into t. Okay. That means if you see this, how you can understand the left hand side is the value of f at a point z naught which is an interior point. Okay. So this right hand side here, this f of z, this is over c. Okay, this is over c. So 1 by 2 pi I terms integration of this function f of z upon z minus z naught dz. Where what is this one? This is point, the point on z. Okay, you are taking point z on this c. Okay, right? That means the value of f, the value of f can be found if we know the value of f of z, okay, on c. So if you know the value of f on c, then you know the value of f everywhere inside of. The value of f, okay, can be found if we know value, we know f on just c. So if you know value on c on this given contour, closed simple closed contour, then we can find, we know the f of f value everywhere inside this c. Okay, and this is one way we can understand. The second one is that if you write this one in other way, that means integration of c f of z upon z minus z naught dz is equal to 2 pi I times f of z naught. Okay. Now again, if you observe this, the left hand side is the integration of some function which is namely f of z upon z minus z. This value depends only on f of z naught. Okay, so that means it is not depending on other values. This is integration of f of z where z is taken on those values. This curve that is same as, you can calculate this as 2 pi I by f of z. Okay, this we use many times to calculate integration of some function. What is condition is required here? That f should be analytic and analytic on in and on inside this C, and z naught should be an interior. Then this integration is same as 2 pi into f of z. Okay, so we'll see these details in detail, but first do the Cauchy integral form. Okay, then we'll see some examples. So theorem, which is Cauchy integral formula. Sometimes we can use CIF. Okay, that's the condition. So what it says is that um, let f be an analytic function inside and on the simple closed contour C. Okay, taken in positive direction. That means counterclock. Okay. Now, if Z naught is any as Z naught is an any interior point of C, then then this f of the value of f at Z naught is 1 by 2 pi I times integration of f of z upon z minus z naught over. Okay, this is the one which we will call it as Cauchy integral formula. Okay, fine. Now, how we will prove? Proof is not a difficult one. If we can understand, as I said, Cauchy-Goursat theorem plays important. From Cauchy-Goursat theorem, last class we have discussed deformation of paths formula, and this result will be proved mainly using that deformation of paths, and later results will be proved using this Cauchy integral formula. So the main central point or one of the interesting result is Cauchy-Goursat theorem. Okay, fine. So how we'll do? Let's again draw this one. So let's draw the picture. Suppose assume that this is our C is taken in counterclockwise direction, and F is analytic on this and as well as inside. Okay. Now suppose our Z naught is any point. Okay, this is Z naught, which is an interior point to this C. Okay. Then if you remember last class, let me show that. That is why it is very important that result which we have discussed in last class. Yeah, here. Principal deformation. Principal deformation of path. What it says here is that if you have a function, analytic function in between these two curves, you have C1 and C2, okay, then integration of f of z over C1 is same as integration of f of z over C. Okay, and we also discussed how this result is useful with an example. Okay, here you can see that if we have any given contour C, we don't know how to find that integration because the parameterization of C may not be easily known. Then what we did with example, we have considered a we have considered a contour C which is known, namely circle, okay, around origin, right? So similarly, that same technique we use here now to prove Cauchy integral formula. What it says here is that we don't know how this C look like. So can we, because F is analytic everywhere here, so if we can find a contour inside interior to C, okay, which contains this Z naught, then integration of F or some function, whatever this function over C is same as integration of that smaller contour. Okay, so the idea is we will consider a circle around Z naught. Okay, so we will consider, if you we can take a contour. Okay, so we'll take another color. So what we'll do is we'll construct or we'll consider a new contour with same orientation. We'll denote this by 0, where this is the distance rho. Okay, that means we will consider and we will make sure that this rho is in small such that this entire CP is interior to this C. That is always possible because from this Z naught you find the smallest distance and you take rho which is less than that smallest distance. See, if you call it D as the smallest distance from Z naught to this curve C, then you take rho which is less than D. Therefore, this will be completely inside interior to this C. Okay, so how we can start with? So we can write the proof. Let C be the given closed contour and Z naught be an interior point to C. Okay. Now we will let or choose choose rho greater than 0 such that the uh, positively oriented circle circle C row, okay, around Z naught. That means with center Z naught lies or 0 around Z naught is interior to, that means it is completely lie inside. No part of C row is on or outside C. Okay, because we can apply now that deformation of path. Right now, since F is analytic everywhere here in between, okay, analytic between C and this C row by by principle of by principle of deformation of paths, we get integration of, see what we want, we are not just taking f of z, we are taking f of z upon z minus z. Okay, that we can observe it is not only f of z, because f of z is analytic inside. Now what can you say about f of z by z minus z naught? Because z minus z naught is inside this c row. Okay, so in between this you can write, instead of taking this f, of course f is analytic, but what we require is the new one, which is f of z upon z minus z. Okay, this is analytic because in between here we are talking about in this, because z naught is inside this one, so there is no problem about f of z upon z minus z naught. Because if at all any problem is here is at z naught, but z naught is in this between inside C row. Okay, so if we consider anything here in this, okay, in between this C and this one, and on this CP and on C, there is no problem. This function f of z upon z minus z naught is analytic. So therefore, by applying principle of deformation of paths to this function, what we get is that integration of f of z upon z minus z naught dz over C. This is same as integration of f of z upon z minus z naught over C row over C row. This is important. Now, what is the advantage? We know what is C row is nothing but mod z minus z naught is equal to row, right? So here you can see that where's this, that means this C row is nothing but all the points z such that mod z minus z naught is equal to, right? That is our C, right? So this can be easily, integration of this can be calculated easily. Okay. Now what we want to find, we want to show that this f of z value is this. That means we will try to see difference of these two. If we can make it less than some epsilon times something, where epsilon is any arbitrary epsilon greater than 0, then these two value will become equal, right? So for that we can check that this minus f of z. Okay, so for that we can also observe that also, what can you say about integration of C row 1 by z minus z? That means in last class we have seen 1 by, using this deformation path, we have seen that one integration of 1 by z, where the circle is around 0. Here circle is around z naught, so therefore it is same as 1 by z minus z naught. Okay, this value we have proved is same as 2 pi I. That easily you can check, okay, by simply substituting z minus z naught is equal to r into e power I theta, then find dz and simplify from 0 to 2 pi, you get. Okay, it is just like the problem which is translated from origin to the center with z, right? Therefore, this implies what we have here is this f of z, f of z naught, f of z. If you multiply f of z naught, implies 2 pi I times f of z naught. That means I am taking f of z naught both sides. So f of z naught I can write inside this is z minus z naught dz over c. Okay, or this is same as f of z naught is 1 by 2 pi I times integration of f of z naught upon z minus z naught dz over c. Remember, we have to prove that 1 by f of z naught is 1 by 2 pi times integration of c. Okay, right? So this we are only up to here. So therefore, if we want to calculate this value, which is integration of this c times f of z minus z naught dz. Okay, so therefore integration of c times f of z upon z minus z naught into dz minus this 2 pi I times 2 pi I times this f of z naught. Okay, if we show that modulus of this value is equal to 0, then we get our result, but which is same as integration of c f of z z minus z naught is same as integration of f of z upon z minus z naught dz over c rho. Okay, minus, and so this, if you don't want, we no need to take this is sufficient. Okay, 2 pi into f of z naught is equal to integration of c rho into 1 by, that means f of z naught, f of z naught upon z minus z naught into d. Okay, so remember, don't confuse this one, with our original result. It is just look like our original result, because our original result we want to show that f of z naught, and here it involves f of z, whereas this one here we have, it is only f of z naught, not f of z. If this is f of z naught, then we are done. Okay, fine. Now if we simplify this one, what we'll get, this is same as integration of the function f of z minus f of z naught upon z minus z naught into these. Right, now somehow we want to make this right hand side whatever by after taking modulus up to this. Okay, this implies modulus of integration of c f of z z minus z naught dz minus 2 pi I times f of z naught. Okay, this is equal to modulus of integration of f of z minus f of z naught, okay, on z minus z naught into d. Right, now how we'll simplify this right hand side using the fact that f is analytic, so in particular it is continuous at z naught. So because it is continuous at z naught, remember this is c rho, whereas this is over c. Okay, so if we take any point, z on cp, then f of z minus f of z naught, we want to make it less than some value. How that is possible? Since f is analytic at z naught, it is continuous at z naught in particular, right? So therefore for given whatever epsilon greater than 0, there exists delta greater than 0, such that whenever mod z minus z naught is less than delta, then mod f of z minus f of z naught, okay, this is less than h. Right, now we have this delta, and we also have this rho, so we have to make sure that our rho is smaller than this. Okay, so that means we have to make sure that our rho, whatever we are having, that is smaller than this neighborhood z minus z naught. Z minus, so this, if you take here, z minus z naught is less than delta, and this is c. Okay, so we will make sure that our rho, the way we have selected rho, is such a way that it is less than that delta, and it is always possible. For example, you can take rho is half of that one. Okay, so we can choose our rho greater than 0 such that this rho is less than 10. Okay, then now if you take any point z, then for any point z on this cp, that means if you take any point z here on this one, so then for z belongs to this c rho, that means we have, this is our c rho, and this is circle centered at z0, and this is distance rho. So if you take any point z here, then what is the meaning of that? Then z minus z0 is equal to, then what we have here is mod z minus z0 is equal to, right? Now as rho is less than delta, this implies mod z minus z0 is less than delta, since our rho we have selected smaller than d, right? So therefore, for all this z belongs to Cp, this condition is true. This implies for all z belongs to this C rho, mod f of z minus f of z naught is less than x. Okay, and if you substitute that here, you call it this as star, then this star becomes, what will become modulus of integration of this. So modulus of integration of this C rho of the function, which is f of z minus f of z naught on z minus z naught, okay, dz. This we know is less than or equal to integration of C rho into this mod f of z minus f of z naught. This is less than, this is less than epsilon, and z minus z naught is exactly equal to this rho, right? And then what we will have, hmm? And length of this curve, because by you need to write like this. So therefore, you write here, this implies mod f of z minus f of z naught, okay, upon z minus z naught is less than epsilon by rho, because this one is z minus z naught is rho. So the maximum value of this function, whatever we are having, is less than epsilon by rho, and that is m. And what is the length of this curve is 2 pi. Okay, so epsilon by rho into 2 pi, right? Sorry, sorry, this is 2 pi rho, right? Not 2 pi I. It is length of this circle, that is 2 pi r if r is the radius, right? Therefore this is same as 2 pi times epsilon, right? So therefore what we have observed is modulus of integration of f of z upon z minus z naught dz over c minus 2 pi I times f of z naught. This value we have proved that it is less than 2 pi epsilon. Now where epsilon is given any arbitrary small number, therefore by taking epsilon sufficiently small, so as epsilon greater than 0 is arbitrary, what we have left hand side on the above inequality, that should be equal to 0. So we get the integration of f of z upon z minus z naught dz over c is equal to 2 pi I times f of z. That is same as, therefore f of z naught is 1 by 2 pi I times integration of f of z over z minus z naught dz over, that proves the Cauchy integral form. Okay. Remember, this can be used several times to find the example. So let's quickly see one example how we can find using Cauchy integral formula integration of given. So for that, let C denote the positively oriented circle mod z is equal to 2. Okay. Then find the integral of z upon 9 minus z square into z plus I dz over this given C. Okay. Now, if we want to use this Cauchy integral formula, what we require is, we require something like f of z, which is analytic, okay, on C and inside C, and we should have some point which is interior to this given C. Then that integration is nothing but 2 pi I times f of that value z naught, which is an interior. Okay, so here we have to, the only trick is how we can select f of z, that is the thing. Okay, so solution, here we can observe that this z minus, so if take f of z as z upon 9 minus z square, then we can see that the problem with f of z analyticity problem is only at z square is equal to 9 or z is equal to plus or minus 3, right? 9 minus z square. So okay, so but mod z is equal to 2. If you take mod z is equal to 2, which is a circle of radius 2 around 0, right? But where will be 3 and minus 3? 3 and minus 3 are outside. Here 3 and here you will have minus. So there is no problem. So f of z, if you take this as z by 9 minus z square, then it is analytic. So f is analytic inside this C. And clearly z is equal to minus I. Z is equal to minus I this here. Okay. Oh, sorry. This is plus I. Yeah. And this is minus. Clearly it is an interior point, right? So what you can write then uh, then f of z is analytic analytic on this C, if you call it this as C, I mean analytic on C, okay, and of course inside also, and inside, okay, and this z naught, which is equal to minus I, is interior to this C, which is mod z is equal to 2. This is radius, right? So therefore by Cauchy integral formula, what we have is integration of this f of z, that means z by 9 minus z square upon z minus z naught, it is z minus I over c dz is equal to 2 pi I times f of z naught is minus. Okay, so therefore this is same as 2 pi I times what is our f of z is this. So f of minus I is z, which is minus I upon 9 minus I square. So 9 minus I square, you can simplify this. It is not at all difficult one. This I and I square, so this is minus I square, which is I square is minus 1, so minus I square is 1. So what you have here is 2 pi and above, and here 9 minus of minus 1, which is plus 1. So what we get here is pi by 5. Okay, so we can use this Cauchy integral formula to evaluate certain types of integrals. So the idea is we have to select suitable f of z in such a way that f is analytic on C and in C, interior to C, and the point which we are considering should be an interior point. That z naught should be an interior to that C. Okay, fine. Now we have this Cauchy integral formula. We have calculated f of z. Okay, this one. This can be extended to f dash of z also, f double dash of z, or your nth derivative of that also. Okay, that means this we can say extended Cauchy integral formula. So that means we can extend this formula for even derivatives of this f also. Okay, we can prove that it is not a difficult one. So extended Cauchy integral formula. Okay. So what is this statement? Statement is let f be analytic inside and on the simple closed curve, closed contour C. Now, if Z naught is uh, interior to C, then this f dash of Z naught, the value of f dash, so it f dash of Z naught, that means we are actually saying that f dash exists at Z naught, and the value of that is equal to 1 by 2 pi I times integration of this f of Z by Z minus Z naught whole square times D. Okay. So not only this, in general, we can do for any uh, second derivative, third derivative, and so on. So fn, nth derivative of f at z naught is n factorial by 2 pi I, okay, integration over f of z upon z minus z naught whole power n plus 1 dz over. So we can calculate if f is analytic, then we can calculate the derivatives of f at any interior point z. Okay? That's why it is the extended version of Cauchy integral formula. So let's prove this. Proof is not a difficult one. It is simple. We can call it as a basic calculation type, and it follows from Cauchy integral formula. And what we want to show, we want to show that f dash of z naught is this. That means we know f dash of z naught is just like f of z minus f of z naught by z minus z naught. That, and you take this difference and show that it is less than epsilon, or uh, when delta z tends to 0, this value is equal to 0. Okay, that is the idea. Now the proof starts with, since f is analytic, okay, and c is this c instead of using z naught, what we do is, because we will instead of writing z naught everywhere, then delta z naught. So just we'll change the notation. Since f is analytic, by Cauchy integral formula, we can write here, instead of using just z naught, we will use the notation z. We'll consider z as a interior point. Since f is analytic, by Cauchy integral formula, f of z, that means our z is interior point. Instead of writing f of z naught, we are writing f of z. That's all. Is 1 by 2 by I times integration of, here we will use now another notation, f of s by z minus z naught. So this is s minus z dx, integration over this. Okay, remember, we have not done anything new. We are where z is an interior point, the interior point as z. That's all. Then s is a any point on the contour. Okay, where s is a any point on the contour. That's simply f in a, we have replaced z naught by z. F of z naught, instead of using f of z naught, we are using f of z here. That's all. Otherwise, we have to take for differentiation delta z, then delta z naught. We can do it here. You, if you don't like, you want to go with the notation, you can take here delta z, f of z naught, then you use z here in place of s, you use z in place of z, you use z naught, and proceed. There is no problem. Okay, just for simplicity, we are eliminating using that z naught. Instead of z naught, we are using z and the other variable as s. That is the only difference. Okay, fine. Now our idea is, we want to show that f dash of z naught, or f dash of z, here z is an interior point, is this way. But what is our f dash of z? Hmm? Our claim. So we can write claim. We want that f dash of z, which is nothing but limit f of z minus of z plus. So here you write z plus delta z. Okay. Just f of z plus delta z minus f of z on delta, as delta z tends to 0. We want to show that this is equal to, we want to show that this is equal to, we are calling it here, which is f of z, which is f of s by s minus z over. So that means what we'll do is, we'll try to find the difference between these two. Okay, and as delta z tends to 0, we want to show that this limit of this one is equal to, that is the idea. Okay, so for that, let's take the picture. Yeah, consider this picture. Okay, so I have taken this picture from the textbook. Okay, image. So what we are going to do is, we have to select, so what are all we require, and we'll try to understand this d. So here, let d be the shortest distance, shortest distance from the interior point z to the curve, this one. Then we'll select delta z, the delta z, okay, such that modulus of delta z is less than this d. Okay, so choose delta z such that modulus delta z value is less than d. Of course, this value is greater than 0. We will take is strictly greater than 0. That is always possible. Okay. Then what is this one? This any point on this curve is denoted by s, and this is the distance mod s minus z. Okay. Then we can observe that for any any s belongs to C, the distance between s and the interior point z is always greater than or equal to d, because d is the shortest distance, okay, from z to that curve. So therefore, if you take any other point on that curve, then this distance is always greater than or equal to d. This information b, okay, and we are make sure that this z plus delta z, okay, this z plus delta z, the distance between these two, which is mod z, is less than delta. So therefore, that point is also inside this C. Okay, that means f is defined there. There is no problem. Okay, so therefore, what we will find, therefore, f of z plus delta z minus f of z upon this delta z, this value, because of using this one, what we will get, f of z plus, so wherever z is there, z plus delta z. Remember, this inside here is in terms of f of s. So there you don't need to substitute. So wherever z is here, we have z is here. Okay. This takes little time. So this z and this will be replaced. Right? So therefore, f of z plus delta z, this will be equal to 1 by 2 pi I integration over C. Okay. F of z plus delta z, which is f of s by s minus z plus delta z. F of s by z minus z. Sorry, this is s minus, right? This is s minus. So s minus z minus delta. Okay? This is f of z plus delta z. Then what can you say about f of z? It is same as f of s by s minus z. Okay, dz. Then what we have here is this delta z. Okay? That we can put it here or here. Is not a problem. I can write like this. Okay, right? Now, if you simplify this is nothing but 1 by 2 pi I integration this f of s. Okay, f of s also we can take outside. So f of s by delta z. Then what is this? Is basically s minus z minus s z plus delta z s minus z into s minus z minus delta. Okay. What we did is we have taken simple LC. That's this. But this is same as 1 by 2 pi I. Okay. This integration of C. This is dx. Remember, this is dx, not dz. Hmm? This is dx. This is dx. Now, this one sz will get cancelled. Dz here, dz will get cancelled. So what is remaining is f of s upon s minus z into s minus z minus delta z into d. This delta z here, delta z, s will get cancelled. This is remaining. Therefore, this is f of z plus delta z minus f of z by delta z. Now we want to have difference between these two values. So therefore, this f of z, f of z plus delta z minus f of z upon delta z minus this value, which is 1 by 2 pi I, 1 by 2 pi I integration of f of s upon s minus z ds over c. Okay, over c, this value is equal to, this is same as 1 by here, 1 by 2 pi I, here also 1 by 2 pi I is there. Okay, then this integration f of s is there. So if you take f of s, then what we have here is 1 by minus 1 by s minus z to s minus z minus delta z. Okay, Now, by this, what we'll have here is nothing but 1 by 2 by integration of c f of s. If you take 1 by s minus z common, then what we have here is 1 minus 1 by s minus z minus delta z, okay, into ds, right? To ds. That you can simplify this is again same as by integration of c f of s, okay, into this s minus z minus delta z we will have, okay, and minus 1. We will get wrong. Yes, we our claim is what? There is some small correction. Our claim is we want to show that f dash of z naught is z minus z naught whole square. That means here we want to show that this is not, this is whole square. Not, nobody noticed it. Okay. So this we want to show. Okay. So that means here we want to take square. So here we want to take one is actually whole square. So therefore this will become 1 by s minus z. Okay. So then you can check that it is just like how we have simplified here, okay, 1 by s minus z and so on. So this, if you simplify, so wherever we do even small thing will be interrupted, right? So this one is nothing but s minus z minus delta z minus s minus delta z. This delta z, okay, is there, right? Delta z is there. Whether we have anywhere any else delta z, no, fine. So this will be delta z upon s minus z. Here, 1 over s is the whole square minus z minus delta z, right? Fine. So therefore, we want to find the modulus of this. This implies modulus of f of z plus z minus f of z upon delta z minus y 2 pi I into integration of f of s minus f of s upon f of s upon s minus z whole square into ds. This value is equal to this one. Okay, that means this is equal to yeah. So this is equal to, if you take modulus, then this will be 1 by 1 by 2 pi into modulus of integration of c this dz into f of s ds upon s minus z whole square s minus z minus delta. That means we want to find the to apply ML inequality, we want to find the maximum value of this one, which is delta z f of s by s minus z square s minus z this, right? For that, now we go back to this picture again here. This second is taking, yeah, little less time. So now delta z mod delta z is less than d, okay, and mod s minus z is greater than or equal to d, okay. So using these two, we want to find upper bound for these values, okay. So what we can observe here is that this modulus of s minus z minus delta z is greater than or equal to modulus of s minus z minus delta z, okay, by using that triangle inequality. But mod s minus z is mod s minus z is greater than or equal to d, okay. So this is greater than or equal to d minus delta z, okay, modulus of this delta z we know, because d mod delta z is strictly less than this, so therefore this is strictly greater than 0, and therefore this delta z, okay, modulus of delta z by s minus z whole square s minus z minus delta z, this value is less than or equal to, and what we know about f of s, hmm? So this we can write as modulus of delta z, okay, which is into mod f of s by mod s minus z. S minus z is greater than or equal to d, so therefore this is less than or equal to d square into d minus delta z. Now, if we let f of s, so let f take maximum value on c, then this above inequality will become less than or equal to delta z into m upon d square into d minus delta z. Okay. Now, you see, I think this is the one where anywhere we missed. Ah, so therefore, this is just like m for new function, and length of this curve, we know length of this curve, our c is, say, let L be the length of the, let L be the length of the contour C. Using all these things by ML inequality, what we get here is this inequality, this modulus is less than or equal to this value, modulus of f of z plus delta z minus f of z of delta z minus 1 by 2 I times integration of f of s by s minus z whole square into ds over c. This is less than or equal to 1 by 2 pi, okay, 1 by 2 pi into this value, which is less than or equal to this times c. So delta z into m, and this is L upon, okay, d square into d minus delta. Now, by taking as delta z tends to 0, we get this right hand side, that is 1 by 2 pi delta z, you can write here ml by this upon d square into d minus delta z. Okay, this everything is finite, but as delta z tends to 0, this will get delta tends to, this entire thing tends to 0, right? So therefore this left hand side, okay, is equal to 0 as delta z tends to 0. That means limit f of z plus delta z minus f of z upon delta z as delta z tends to 0, this is equal to 1 by 2 pi I into integration of f of s by s minus z whole square. Okay, that as implies f dash of z is equal to 1 by 2 pi I into integration of f of s upon s minus z whole square dx. Okay. Now, same way you can do it for f double dash. If you want to do it for f double dash, you want to differentiate this one. Okay. I can verify, I can ask you to verify that f dash, verify that f double dash of z 2 by 2 pi I. Okay, integration of f of s on s minus z whole cube into dx. How we can do this? Just like how we have find the difference between this one, and we already have f dash of z here, which is in the form of Cauchy integral formula type. So just find f dash of z plus delta z minus f dash of z upon z plus delta z minus this 2 if at all it get cancelled, this f of s by s minus z whole cube dx. This show that, okay, whatever, find this value. So find this value and show that this tends to 0, whatever we are having here, this tends to 0 as delta z tends to, then we will get this f double dash of, okay, by induction, f nth derivative f n of z, okay, or if z naught is an interior point, that you can replace this or you can put it like there is no, so f is equal to n factorial. Next time if you see here 2 into next 3 will come, okay, Next time 2 into 3 and so on. So that is why you will get n factorial into 2 pi I integration of f of s by s minus z whole power n plus 1. This is the formula of nth derivative of f evaluated at an interior point z. Okay. If you use z naught here, then you use here z. That's all. Okay. This is about the Cauchy integral formula and its extended form of Cauchy integral formula for derivative. Okay. We'll see some consequences of this Cauchy integral formula in next. Okay. We'll stop here.